Welcome to Finite Element Methods. Today we'll be discussing the analysis of wing composites, and we'll be going first through a theory, and then Lifu Wang will guide us through the ABAQUS tutorial. So first, I'll highlight my book on this topic is the analysis of metallic aerospace structures, and in here we discuss how you have four different loads, several loads acting on a vehicle, and they act on the aerodynamic center. You have the lift, the weight, the thrust, and the drag. And the lift usually uh, acts in the direction perpendicular of the flight path. And the drag is caused due to skin frictions that occur, and due to all other mechanisms like turbulence. Here you can see that we have a wing, and the wing typically has a cross section that has this shape. And this cross section is very nice because it provides that ability to provide the lift required to keep the aircraft floating. And to be able to take the loads of aerodynamic loads, typically these wings have, for example, ribs and then spars. And these ribs provide the shape of the wing, also prevents some amount of buckling. And the spars provide the stiffness required so that you don't have a catastrophic failure of the wing. Also, you have this particular outer shell that can also provide the additional stiffness required. In addition, you also need some stiffening elements near the engines because you have engines connected there. And so, at the end of the day, this wing is then connected to the fuselage there's many different ways to do that. Here, what I'm showing is a NACA 2414, and they're all come in different shapes depending upon what performance you need. So here's some more nomenclature. You have the thickness of the airfoil. You have the lift, the weight. You have the angle of attack. So if this is the uh, flight path, the drag acts perpendicular or parallel to the flight path, and then the lift acts perpendicular to the flight path. The angle of attack is the angle between this chord line and the flight path. That angle is going to change the amount of lift. So if you have more angle of attack, more lift will occur. If you have less angle of attack, less lift will occur. There is an angle at which, however, if it reaches at a very high angle of attack, that in that case you start to lose all the lift and you stall. But typically, these are the loading conditions acting on the vehicle. And here I'm going to show a quick video of an airfoil in a wind tunnel test. And that's what's going to help us really characterize the behavior of a lift. And what you see here is a wind tunnel test. Usually, powder or some fluid is passed through. And you can see here the angle of attack is being changed. And they're measuring forces and things like that. You can see here you start to have flow detachment in this area, and here you're going to have a stagnation point over here. Here's another video. You can see as the angle of attack increases more and more, the flow detaches a lot more, and then you could reach a condition where you start stalling. No more lift will occur, and the stagnation point is over there. So lift depends on the density of air, the square of the velocity, the air's viscosity and compressibility, the surface area over which the air flows, the shape of the airfoil, and the aircraft's inclination to the flow. And so one way to deal with the complexities associated with all these different parameters, there is a single variable that can help capture all that, and that's usually the coefficient of lift. So this testing here usually uses the coefficient of lift information to kind of study the problem. As you can see, the angle of attack increases from 0 degrees. So I'm looking at this angle here. So this angle of attack 0 degrees. So now this camber is aligned with the relative wind. In those cases, the lift coefficient is smaller. But as you increase the angle of attack, the lift coefficient increases until it drops off because you have too much of an angle to the point that you have float detachment, and you no longer can sustain lift or produce lift. You can see here a high pressure environment here. You can see the pressure changes over the airfoil. We're going to make an assumption later when we do a structure analysis, assuming we're going to assume that the whole bottom surface has that pressure applied. And it's just an assumption. Typically, what you like to do is apply a non-uniform pressure across. And that'll be the preferred method. If we can get that into ABAQUS, that'll be great. But for now, we're going to assume there's a uniform pressure distribution. In real life is non-uniform with the highest pressure right about here. A high pressure region here, low pressure region here produces the lift required to really keep the aircraft flying. And so here you can see a lift force equals 1/2 rho, the air density times the velocity squared, the stream velocity squared. And this right here is a dynamic pressure times the span area of the wing times the coefficient of lift. And so this, again, you can find through the wind tunnel test. So in reality, a lift then depends on this coefficient of lift, which depends on the angle of attack and the span area and the velocity of the aircraft. If you have a steady, straight, and level flight, you can then calculate the lift as this equation here, and the lift is equal to the weight of the aircraft in this scenario. So you can actually calculate the weight of the aircraft if you know your steady, straight, and level flight. If you have the span usually is fixed and the weight is known. So you know what velocity you need to be going at in order to keep that to be true. Here you have a pull-up maneuver. At this location, when you have this pull-up maneuver, you're going to have an amount pulling against here, the center of where we're rotating the aircraft about. And that centrifugal force is going to cause a load factor. So the lift is going to be quite significant compared to the weight. And so if you're going this airspeed, and that's the radius, and that's the acceleration, you can actually calculate that the lift is about 3 times the weight. So that's going to will load up the wings 3 times the weight. So that's a lot of loading there. For category aircraft, there's a limitation of what load factors you could have. We're okay for this type of U.S. transport scenario, but we are exceeding this one, for example. I'm just showing this as an example, but the FAA regulates these load factors for various situations. In the analysis we'll be looking at, we'll be looking at a true airspeed of this amount. The angle of attack is 5 degrees. The coefficient of lift is determined from wind tunnel test as 0.7 at 5 degrees. You can see that here. At 5 degrees is about 0.7. Not perfect, but that's just an analysis that we're going to do. And then we can calculate the lift divided by span due to steady state flight. And that basically comes from this equation. We know the density, we know the velocity, we know the coefficient of lift. So with this information, I know the lift divided by span. For the pull-up maneuver, we have calculated a load factor of 3. So I can then apply this problem. We'll simplify the problem by applying a uniform pressure on the bottom surface of the wing to simulate lift using the following formula. So I'll apply pressure on the bottom of that wing, and that's going to be equal to, this should be lift divided. And so we have the pressure on the wing will be lift divided by span, which is weight divided by span times the load factor. The load factor was calculated as 3 for the pull-up maneuver. So I'm going to apply a pressure on the wing, and we're going to do uniform pressure, which we know is not correct 100%. But that's how we're going to go about that. And we're going to design a wing that can take this loading condition. And the whole point is to show how ABAQUS, how we're going to put this into ABAQUS, how we're going to simulate the conditions, and how we're going to design the composite structure to handle these loads. But in general, I'm going to pass it over to Lifu, who is going to guide us through this tutorial. And that's very exciting.